Lesson 6-8, roots and zeros. We're going to determine the number and types of roots for a polynomial equation and then find all of the possible zeros. So we've already learned that a zero of a function is any value c such that f of c equals 0. When we graph the function, the zeros are the x-intercepts of the graph. So here's kind of the key concept that relates to zeros, factors, and roots. So if we have a polynomial function, then the following statements are equivalent. They mean the same thing. C is a zero of the polynomial function f of x. Then that means that x minus c is a factor of the polynomial, and c is a root or solution of the polynomial equation f of x equals 0. In addition, c comma 0 is the x-intercept of the graph. So if we have this graph here, it's a degree 4 polynomial function. It's got 4 real zeros at -2, -1, +1, and +2. That means that the factors of the polynomial function that is graphed here must be x plus 2, x plus 1, x minus 1, and x minus 2. We also know that the solutions to the equation f of x equals 0 are x equals -2, x equals -1, x equals 1, and x equals 2. So that's how zeros, factors, and the solutions are all related. Now let's solve each equation here and then state the number and types of roots. Well, we can definitely pull off the real solutions from the graph by finding the x-intercepts or the zeros, but in this particular case we can also factor and find our solutions. So I've got a trinomial. I'm going to try to factor it into 2 binomial factors. X squared factors into x times x. 16 is 4 times 4, and I'm going to make them both negative because -4 and -4 adds up to -8. So my 2 factors are x minus 4 times x minus 4. Now, this factor is repeated twice, so when you solve it, when you set it equal to 0 and solve it, you only need to do it once. We've got the 0, x equals 4. Now, because I've had 2 factors here, x minus 4, x minus 4, and they both give me a solution x equals 4, there's only one real root here, but it's a repeated root. So we call it a repeated root or a double root if it happens more than once, like in this case here. In terms of the graph, what it means is we've got a 0 at x equals 4, but it's where the vertex of the parabola hits the x-axis. That's why we only end up with one real root. Here's another example. Whoops. X to the 4th minus 1 equals 0. Now, x to the 4th minus 1 is a difference of 2 squares. So I can split it into 2 factors, x squared minus 1 and x squared plus 1. Now, x squared minus 1 again is a difference of 2 squares, so I can split it into x minus 1 times x plus 1, and then I still have the third factor, x squared plus 1. Great, now this is as far as I can go with the factors, so I'm going to set each factor equal to 0. So x minus 1 equals 0, x plus 1 could equal 0, and x squared plus 1 could equal 0. Now we solve them. In the first case, we get x equals 1. In the second case, I'm going to subtract 1 on each side, so I get x equals -1. And over here, I'm going to subtract 1 on each side to get x squared equals -1. And then to undo a power of 2, we're going to take the square root of each side. So x equals, remember that your square roots are positive and negative, and the square root of -1 is I. So we've got plus or minus I that represents 2 other solutions here. Okay, so we have 2 real solutions or roots, +1 and -1, and we have 2 imaginary roots, +I and -I, for a total of 4 solutions. Let me show you one more of these. So we've got x to the 3rd plus 2x equals 0. The first thing that I notice is that there's a common factor of x in each term, so I'll factor out an x. Now what's left in parentheses is x squared plus 2. Now I can't factor that any further, so these are the 2 factors here, x and x squared plus 2. Let's set them equal to 0. So x equals 0, and x squared plus 2 equals 0. This first one is solved already. X equals 0, that's one of our roots. In the second case here, I have to subtract 2 on each side to get x squared equals negative 2. Now we're going to take the square root of each side. I know that my solutions here are imaginary because I'm taking the square root of a negative number. So we get x equals plus or minus. Now think of this as the square root of negative 1 times the square root of 2. The square root of negative 1 is I, so I can pull that out. And the square root of 2 just goes behind it. So I've got plus or minus I times the square root of 2. Okay, we have a total of 3 solutions here. There's one real solution, 0. And there's 2 imaginary solutions, positive I square root of 2 and negative I square root of 2. So we've got 2 imaginary solutions. Now what we notice in the last 2 problems here is that the number of roots actually equals the degree of the polynomial. X to the third here, that tells you that there's a possibility of 3 solutions or 3 roots. They're not all real, they're not all imaginary, but in this case we had 1 real and 2 imaginary. In example B, we had a 4th degree polynomial. There were 2 real roots and 2 imaginary roots. So most of the time your degree of the polynomial tells you how many possible roots you have. Okay? All right, let's move on to something else. So here's another key concept from this section. It's called the complex conjugates theorem. So suppose a and b are real numbers and b does not equal 0. If a plus bi is a 0 of the polynomial function, then a minus bi is also a 0. Basically, if you know that one complex number is a solution, its conjugate is also a solution. So if a plus bi is a solution, so is a minus bi. All right, so here's the last example. Write a polynomial function of least degree with integral coefficients, the zeros, which include 3 and negative 2i. Now this is kind of a lot of words in this direction here, but we want to write a polynomial function. So you're going to choose a variable. I'm just going to use x. Of least degree, that means the lowest degree possible. Integral coefficients means that the coefficients in front of our variables are positive or negative numbers, no fractions, no decimals, they're integers. And the zeros include 3 and 2 minus I. So I know that one solution is x equals 3. Another solution is x equals 2 minus I. And by the complex conjugates theorem, that means x also equals 2 plus I. 2 minus I is a solution, so is 2 plus I. So I know that I've got 3 zeros to this polynomial function. So what does that mean about its factors? Well, if I set these equal to 0, x minus 3 equals 0, that tells me that x minus 3 is a factor. If I set this middle one equal to 0, I'm going to subtract 2 and add I to set it equal to 0. So that means x minus 2 plus I is a factor. And if I set this last one equal to 0, I'm going to subtract 2 and subtract I to get it set equal to 0. So x minus 2 minus I is my last factor. Okay, now what we need to do is multiply all this out. It gets kind of messy because we've got a lot of terms here, but let's go ahead and go through it. So I'm going to leave x minus 3 alone for right now. I'm going to leave that out in front, and I'm going to multiply these back 2 together. I need to do a lot of distributing here. I'm going to start with x and multiply it by x, negative 2, and negative I. So I'm going to start by distributing x through to the last polynomial here. So x times x is x squared. X times negative 2 is negative 2x. And then x times negative I is negative ix. Then let's move on to the middle term, negative 2. We need to multiply it by all 3 terms in the back polynomial. So negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times negative I is positive 2i. Now finally we're going to multiply I times everything in the back polynomial. So it's I times x, positive ix. I times negative 2 is negative 2i. And I times negative I is minus I squared. So now I've got all that multiplied together. Now I'm going to combine like terms. So again, x minus 3 will hang out in front for right now. Let's put all the like terms together in this polynomial that we've got here. I've got 1x squared. I'm going to cross them off as I use them. I've got negative 2x minus 2x. That's negative 4x. I've got a negative ix and a positive ix. That makes 0. Those cancel out. Then I've got a positive 2i and a negative 2i. That also cancels out. And I've got 4 minus I squared. Now remember that I squared really is negative 1. So I've got 4 minus negative 1. 4 minus negative 1 is positive 5. And now I've got everything combined together. Okay, now the next thing I need to do, we're not done yet. I actually need to multiply by x minus 3 now. We've got to multiply everything out before we get our polynomial. So now I'm going to distribute x times x squared minus 4x plus 5. And we get x to the third. Then x times negative 4x is minus 4x squared. And x times positive 5 is plus 5x. Now we're going to distribute the negative 3. Negative 3 times x squared is minus 3x squared. Negative 3 times negative 4x is plus 12x. And then negative 3 times 5 is negative 15. Hopefully you see where I've gotten all those terms from. Okay, now we're almost done. The last step is to put together any like terms. So I've got an x to the third. I've got negative 4x squared and negative 3x squared. That's minus 7x squared. Positive 5x and positive 12x is positive 17x. And then there's a minus 15. So here's my polynomial function. It's got integral coefficients. It's degree 3. And assuming I did all my math correctly, it's got 3 zeros. 3, 2 minus I, and 2 plus I. All right, now here's a couple for you to try on your own. Number 1, I want you to solve the equation. You can factor it. You've got a difference of 2 squares here, and then state the number and types of roots. Number 2, follow the last example I just did. Write a polynomial function that has zeros negative 1 and 1 plus 2i.